right. Hey, everybody. It's really great to be here today. Thanks so much for having me. As Patrick already said, my name is Monica, and I'm working as the lead front-end engineer at SumUp. You may have not heard of us. We're not very good about talking about ourselves. But today I'm going to share some of the things that I have learned over the last 4 years working at SumUp. And to give you a bit of context from where I am approaching this topic, I actually joined SumUp when we were only 80 people, which by some measures is maybe already pretty big. But today, now, we are more than 1,200 people worldwide. So I have seen a huge transformation and a huge scaling up of the company, and I'm going to share some of the things that I've learned about how to build architecture in a way that allows you to add new people to a project and implement new features in a scalable way. So today I want to start first with a question, and that question is, why do we rewrite software? I don't know about you, but I feel like I am rewriting software all the time. There are features that I have implemented so many times over the last years, especially because I've been at the same company for a few years. I've had a chance to see how this happens. And I think there's not just one reason why we normally rewrite code. In fact, there are a lot of different reasons why we decide that it's time for that code to be rewritten. To illustrate this, I want to share with you my first ever experience as a developer rewriting code. So I was 19 years old. I got my first real tech job. My job title was Student Webmaster, which is an amazing job title because you are both student and the master at the same time. It doesn't get better than that, right? So I was a student webmaster. I was 19. I thought I had 4 years of experience because I started to learn PHP when I was like 15. So I had some reality coming for me. So I was hired at this job to write PHP and MySQL. And what happened on my very first day is I inherited a code base from the previous student. But that student was writing object-oriented PHP. But the PHP that I knew was, okay, here's a template. I make some SQL calls. I render it in a table. And that was pretty much what I knew how to do. I could build basically anything using this small subset of tools. So I looked at this object-oriented PHP, and I had no idea even how to deal with it. Like, I just didn't even know what are these arrows and things. I had no idea what it was. So how did I handle this? Well, I decided it was time to rewrite that code because I just didn't understand it, so I had to rewrite it. And I think a lot of code that we have these days, it gets rewritten because people are just inexperienced. They don't know how to even understand what the code was originally doing, so they say, well, that's the only way I'm going to understand it. It's got to be rewritten. I think another big reason why code gets rewritten is because it's fun. I mean, how many people spend their Christmas break migrating their static blog to the next static site generator? Anybody? Is it just me? Yeah. Okay, so that's like the time of the year. I write my 2 blog posts of the year, and I also update the layout, everything like that. We do it because it's fun. And frankly, I think we should admit to ourselves a little bit more that a lot of the code we rewrite is probably because it's fun. One really nice reason why code gets rewritten is because at last there is a better solution available. I remember when I came into my job at SumUp, they were using Angular. Angular was cool back then, by the way. So I was like, okay, we need to do some lazy loading. But that was really hard in Angular 1. So I hacked some things together, made it work. But nowadays, lazy loading of different pages of your single-page application is supported in a first-class way. So all that kind of stuff, we can replace it. And it's amazing when at last there is a better standardized solution available and you don't need maybe the hacks and workarounds that you were using before. But I think the main reason why code gets rewritten, or at least why we all say we need to rewrite code, is this last point. And that is technical debt. Technical debt, right? So when you decide you need to rewrite code, you often say, there's so much technical debt, I cannot do anything else but rewrite it. But what actually does technical debt mean? I think if I were to ask the different people in this room, you'd probably all give me a little bit of a different answer. Is it code that I didn't write? I think it's very easy to label code that you didn't write as technical debt because maybe you're inexperienced or you're just too lazy to understand it. Yeah, it's very easy to say that over there is technical debt. Or if you're like me, you've been somewhere for a while, you've seen the impact of the code you've implemented. It might be code you wrote before you knew what you were doing. And now that's technical debt, and because you're still here, you gotta pay it. Some people may also say that things like old libraries, outdated dependencies may be some kind of a debt because perhaps it slows you down. And another kind of technical debt that maybe people don't think about very much could be features no one uses, because actually you end up migrating that code all the time, you bring it with you through the years, and yeah, maybe the value that's being delivered by that code isn't worth the investment that you take in maintaining it. So if I were to define technical debt for myself, it would be something like this: code, tools, or infrastructure that negatively and repeatedly affect the speed or quality of delivery. And we know what technical debt looks like. It looks oftentimes something like this. When you begin a new project, the speed of adding new features is amazing. There's nothing at all to stand in your way. But over time, it can feel like the speed is really decreasing, and in the worst case scenario, you actually reach a point where it feels like you have hit rock bottom. But there is an even better model to think about this with. So imagine you are working in this app. Okay, it was fast, now it's slow to add new things. And you do what any developer does when they reach this valley of despair. And that is, you make a case for your refactor. You say, I finally understand what I need to do. I understand the business domain, I understand the problem, I understand maybe what the user needs to do, so I refactor it. But unfortunately, it often happens that your refactor is not as good as you thought it was gonna be, right? And maybe you look back at the previous implementation and you say, whoops, maybe it wasn't so bad. Actually, that one had less bugs maybe because it stood the test of time. And I like to call this recurring technical debt, or technical debt on a subscription model. And you want to think, oh my God, like how can I cancel my subscription to this technical debt? And to make it even more depressing, there is an official term for this phenomenon. It's called the second system effect. Maybe you have heard of it if you've read the Mythical Man Month. And it's basically exactly what I described. You have something that it works, it's successful, and we tend to think, now I know how to do it better, so I'm going to replace it with something else. And that thing tends to be really over-abstracted, over-complicated, because you are basically too confident that now you have all the perfect abstractions you can apply to that problem. There's also this great quote by the inventor of C++. Legacy code often differs from its suggested alternative by actually working and scaling. So this is, for me, very depressing, right? Because you think about the situation we are in as software developers. So you have some code. It's gotten to a point that you're feeling very slow implementing new things. You think, at least I can refactor this. I got some time from my PM or my tech lead, and you go and do that, but you're very, very likely to end up in an even worse place than you started. And the first thing that comes to my mind here is this image of the snake that eats its own tail. It's like the symbol of infinity. And you have to wonder, is this my destiny as a software developer? I just rewrite this stuff all the time, and I don't feel like I'm moving forward. I just rewrite things. And that brings us to the hard fact of software development, which is that the real cost is not in the initial implementation. It's in the maintenance, because the first time that you implement it, it's very rarely over. You're going to have new requirements, the market changes, new laws are introduced, whatever it is. So the question is not really, why do we rewrite software? Sometimes there are really great reasons for that. But in the case where we have to rewrite things because our original code was maybe too brittle or not prepared, how do we make our systems more resilient to this inevitable change? So that instead of having a graph that looks like this, where we become sad because everything is slow and it feels like you can't move, you end up with something more like that, where in fact You start to put in some infrastructure early on in the application that helps you to even accelerate your speed of delivery. How can we get there? So how do we get there? I mean, this is a question, I think it's one of the timeless questions of software development. And the typical answer is something like this: good architecture. But this is like the worst answer, right? It's super unsatisfying. And I think there are a number of different reasons for why just saying software architecture is like the panacea for everything is not something that makes us feel right in the world. The first thing I think is that architecture has become kind of a dirty word. It sounds kind of elite, you know, it's complicated to spell maybe. I think a lot of people don't even work with software architects, so you might wonder, what do software architects even do? We know that they have like transcended coding into some higher plane, but we're not really sure what they do over there besides maybe making some UML diagrams, not clear. And then architecture itself, it doesn't even have a shared definition across all of software development. You think about how in frontend and in JavaScript you have the flow people, and you have the TypeScript people, okay? And even within JavaScript, we can't get people to agree on the best approach. So why, in the whole realm of software development, would we be able to have people agree on a standard definition of software architecture? I mean, it's impossible. Making developers agree on anything can feel impossible. And at the end of the day, it feels detached from daily problems. So you're working as a developer in a code base, and you're struggling because you need to change the behavior of a button. You need to make that button do something different than it used to do, and that person who wrote the code before you is making it very difficult. And, you know, when you say, well, good architecture would have solved that problem, it is like the most unsatisfying thing that anybody can even say to you. So instead of trying to think about what's a new, better definition of architecture that I'm just going to make up on the spot, I want to reframe the way that we're thinking about architecture instead as something called enabling constraints. Maybe you have heard of this term before. I learned about it a few months ago, and I thought to myself, this is like the perfect metaphor for how I see architecture. So enabling constraints, it sounds a little bit like an oxymoron. How can you have constraints that also enable you? But that's the beauty of it, I think. So we're going to talk about architecture as constraints on how we use data and code that are going to help us to move faster and safer over time. And to give you an idea of what enabling constraints really means, I want you to think about this example from the real world. So imagine you are in your car, and you are driving down the Autobahn, okay? And on the Autobahn, there are some places that have no speed limit at all, which for me as an American is a horrifying concept, but it exists and people survive this, right? So when you are in your car driving on the Autobahn where there is no speed limit, the only limit to how fast you can get down this road is the speed at which you feel comfortable operating your car. There is not really anything else going on there. And the question is, why do we actually feel safe to travel at those kind of speeds? I would argue that a big part of that is because we have some serious barriers in place. So if I am driving really fast in one direction and someone else is driving really fast in another direction, they're going to have a really hard time getting into my lane. Maybe with a whole lot of determination, but it's pretty hard, right? And that's one reason why we feel safe. We also have some conventions that help us to feel safe too. You think about where the slow people go and the fast people go, right? So you have the slow people driving on the right, and the fast people are able to pass them on the left. So in this way, we also have constraints on the road, the way that we use it, that enable us to feel actually safe moving at these ridiculous speeds. And I think the same thing has also happened when you look at programming paradigms. Over time, we have found more ways to constrain ourselves that actually enable something completely different. So think about object-oriented programming. This was a departure from structured programming, so you no longer could just say, hey, go here, go there, you know. We decided go-to was considered harmful because actually it was too powerful and we needed to constrain ourselves. So instead, all of our code needed to be organized into classes. which can feel a little bit tedious when you are not used to this, but as a result, we actually ended up being able to have independently deployable subcomponents, because finally, the structure of the application and the source code could be separated a bit. So we gave something up, this kind of power of being able to go absolutely anywhere, and we got something really meaningful in return. Perhaps these days people are more familiar with functional programming. In functional programming, we had a very similar phenomenon. Probably the most noticeable constraint in functional programming is that we give away our ability to mutate data. And strictly speaking, mutable data is more powerful than immutable data. You can do more with it, right? Immutable data is all about saying no, right? So, but what did this give us? It gave us safety. So finally, we wouldn't have these race conditions anymore where your data changes out from under you because somebody else started to operate on it. So you don't need these kind of locks in your code anymore that you used to. Think about how transactions work in a database. It's a similar concept because we are mutating data in the database, so we need this transaction, right? Or we need, or even better, the read lock. So yeah, you can see there are all kinds of problems that are in fact solved by having immutable data. And I think the trend has also followed to front-end development. So a really simple example, let's look at var versus const, right? So we stopped using var and now we use const. It seems like a simple change, right? So we're not reassigning our variables very much anymore, but as a result, it's a lot more predictable. When you read a function and you see something is declared with const, well, you're not so worried that it's going to be radically reassigned somewhere else in the function. Think also about the transition from DOM manipulation libraries like jQuery to tools we have today like React. Strictly speaking, we gave away this kind of DOM surgery approach that we used to do, where you're fiddling with individual nodes, adding, appending, and removing and mutating them. And instead, in return for being on a higher level of abstraction, we get more predictable UI. You can test it. It's incredible. But we did that by giving away a little bit of power. And yeah, here's another one, which I know it has been a little controversial lately on Twitter. Yeah, so I don't really have something like strong to share there. I like to avoid these kinds of discussions, but I did notice in the last year of working with CSS and JS how it helped me to feel a bit safer. Because instead of being able to rely on some global names that exist in the namespace and being able to write components and say, I know those classes will be there, so I will just use them. You can't do that anymore. So you don't get to rely on these kind of global side effects. And as a result, your code is a lot safer because you can actually combine the component and the classes right next to each other. And if you're working in a team that uses really great naming conventions, well, that was even sometimes bad, right? When you're working in CSS, because maybe two people are just using the same class name. So all in all, what I want to say here is that we are constraining ourselves all the time, and constraints are great, right? We're opting into these constraints. So we're not looking for more ways to become more powerful developers. In fact, we're trying to figure out how to give away the things that we used to use to shoot ourselves in the foot. So we trade these constraints for safety and for speed and for a whole lot of other benefits. So today I want to talk about 3 specific constraints that you can use in your applications for having code that is going to be easier to change and more adaptable over time. And of course, I should mention, it's not exhaustive. There are a lot of great books and talks about architecture, but I'm going to focus on a couple of the things that I think made the biggest difference for us. So we're going to go through these 3 constraints, and then we're going to talk about the specific things that they enable. The first thing is about source code dependencies. So a lot of times, I think people get really hung up talking about directory structure. But the reality is directory structure is maybe nice for us developers, but it doesn't really tell you about how things depend on each other in an application. So there are a couple of different ways how our dependencies in our applications, our internal dependencies, are usually organized. Perhaps this first one is the one you're most familiar with. It's the so-called ball of mud. All right, and if you don't have any strict rules in the applications you're working on what may depend on what, there's a very good chance that this is what you are experiencing at the moment. So there are no rules. Anything can depend on anything else. Doesn't really matter. You also have a layered approach where the application is divided into clearly defined layers, what may talk to what may pass through what, and so on, and it goes in a single direction. And you also have a modular approach. Now, I'm sure a lot of us like to think our code's modular, because I use modules, of course. But what I mean here is something more like packages that have clearly defined finite APIs, and that actually hide a lot of things privately to the package, but we're not going to talk about that today. We're going to focus on these first two things. So what actually is the difference between having the ball of mud and having a layered approach? Well, think about what happens when you change something in your application. What happens when you're in the ball of mud? Do you have any way of even knowing what potential side effects there could be? You don't know, right? Anything else could be importing that thing. You really have no clear idea what is depending on what. And the fact is that you end up with a potential scope of regression that is undefined, let's say. It could be very small, it could be very big. You have no certainty about that. And even if you tell QA, like, I'm sure it's a small change, like, you don't really know, right? And as a result, you often end up with cross-team conflicts. If you have multiple teams working in the same code base, well, one team is going to be really unhappy when the other team introduces a bug that affects them, right? Because you have all of these cross-dependencies. But think about what's happening when you're working in a more layered approach. You have a change that is introduced, and you can actually, within reason, say, I have a limited potential scope of regression. And this means that if your application is organized in a way that reflects roughly your team structure, then there's a good chance you're not going to affect other teams. So this is really the key difference between having a ball of mud where anything can touch anything else, and also something that is a well-organized, but still it's a monolithic application, comes down to the internal dependencies. So let's just take a super quick look at how this could look with an application structure we are a little more used to. So usually start, right? Your router is where everything is stemming from. You perhaps have an API or a data layer where everything there is separated, and then you get into your UI. Okay, and probably you have different pages, you might have different subpages and subsections. But the important bit here is that for each of these pages, the rest of the application may as well not exist. Now, this is like something that maybe is a little bit radical, but the fact of the matter is that this is the only way to actually feel certain that when I change something on one page, it's not going to have some completely bizarre side effects somewhere else. So by actually being mindful of the direction that our dependencies are pointing and controlling them, we have a way to isolate changes. And this is something that is really important when you have a larger team working in a shared code base, shipping things in parallel, doing a continuous delivery cycle. So the first thing you might think is, what about shared components? Because we love to share components, right? A lot of us are writing React, maybe Vue. Components are like what we love, and sharing them makes us feel like we are good people, right? I made it shareable. It feels really nice. And for this one, I personally take a pretty hardcore approach. May or may not work for you, but depending on how your teams are structured, I think this makes a lot of sense. I really believe that purely presentational components belong in your design system, and if it has business logic in it, there is a very good chance that those things are not quite as the same as you think that they are. And copying and pasting them might be a better approach than putting them into some nice shared directory. And we're going to talk a little bit more about this now. So the next constraint that I want to propose is being a little bit more conservative about code reuse than we have been traditionally taught to be. You know that in programming and in software development, we love dry, right? It's like endorphins. You see something and you're like, I can make this a function, and I can extract that, and then I suddenly have less code, and it's like a high. You get super excited about it, and you feel like you've done your deed. Like, I was a good programmer today, It's very fulfilling. But the reality is that sometimes we apply this dryness in a way that results in code that is very brittle and code that is prone to introduce side effects. And we do that because we say code reuse is the most important thing, and that is like my guiding principle. It's like my lighthouse. But I want to think with you guys a little bit about the impact of time on shared code. So imagine you're making a new feature, and your feature needs a component that looks really similar to a component that lives on another page. And you're like, maybe I can take that component, I can generalize it a little bit, I'll put it in the shared directory, and I'll just make both things depend on it. Fabulous. I even feel like I've done a service to the code base, you know, like I'm a good citizen. And that's nice. So now these two features both depend on this shared component, which maybe has a bit of business logic in it. But what tends to happen over time is that this component wants to do what is known in biology as a mitosis. So it wants to separate, you know? It kind of no longer has the same identity that it used to. And these use cases that each of these pages maybe require begins to diverge. And you'll notice this in the code by a couple of signals. It says something like, if I am on this page, do that. If I'm on this other page, maybe do something else, right? So you end up that this component needs to become aware, where am I in the world? And you begin introducing branching into this component, and it becomes a lot more complicated. And now your component is not as general as it was when you made it. In fact, it now only really works in those two spots, right? And I think this is something that happens to us a lot, and the big problem is that nobody is going to see that code that wants to mitose and help it to mitose because they feel bad, you know? They feel bad to move something away from the shared directory because then other people can't use it. God forbid. And the point I want to make here is that it's so much more important that code remains decoupled than it is that the code remains dry. Code reuse in and of itself is not the goal. The reason we want to reuse code is to reduce bugs that are introduced by duplication. But if we introduce more bugs and more side effects by sharing things, then we are completely defeating the point why we started to do code reuse in the first place. And there is a fabulous tweet that I saw that really illustrates this point for me. It says, a regular person either sees the glass as half full or half empty, but the engineer sees both glasses and tries to learn in what context it makes sense to see it half full or half empty. And the point that I want to make here is that sometimes you just need two glasses, because two people need to be able to drink water at the same time and not know about the other one. Or maybe they need to drink something different. The fact is that sometimes duplication is going to lead to a better and more maintainable code base. So by being a little bit more conservative or skeptical about when code should be reused, we can avoid coupling together code that will ultimately, very likely, diverge over time. And the very last point that I want to talk about today is about enforcing your boundaries. So I don't know how it works at your company, but oftentimes when you make architecture decisions, you do something really nice and you document it. Maybe you put it in Confluence. Maybe you write a wiki page. If you're feeling fancy, you make a diagram. Maybe you even use Sketch because you're fancy like that. So you document it, you put it there, and you say, aha, I have made this choice. Amazing. We're never going to have this problem again. But the reality is that no developer is going to go into your dusty wiki page, you know, clean it off and say, I'm going to build a feature. I better consult this diagram first, right? It's just not how we work. So how can we actually make sure that our architecture is followed when nobody is going to go into the wiki and read this diagram? I mean, I'm not saying you shouldn't make a diagram. It's very helpful for onboarding people, but you shouldn't rely on them to actually do that before they begin to code, you know, the first thing in the morning. So let's imagine you have an application. It looks something like this. You have some different pages, subcomponents. You are sharing business logic, and you go through and you snip out the things that shouldn't know about each other, and perhaps you even duplicate a little bit of business logic in these two pages. And ultimately, they start to diverge a little bit because they become more specialized to the context that they both exist in. But what happens when a developer comes along and that developer was not in your architecture meeting and they're not reading the wiki page, but they see these two pieces of code and they have that euphoric feeling, right? They have that feeling, I could abstract that, right? They see those two things and they think, I can do a good deed for this code base. It is my duty even to do that. I mean, it's true. Probably we all feel this way, right? I have to do it, you know, and you want to say in some way, please don't help me, you know? So how can we do that? So there's a really neat tool or concept called forbidden dependency tests. And what this allows you to do is to essentially assert that one subtree of your application may not depend on anything outside of that subtree. Or you can do it in the inverse way, and you can say, I am this subtree, no one may depend on me, which is great, because then you know you can have certainty that if I change this, no one is going to come tap me on the shoulder and be like, you made me a JIRA ticket. So this is pretty awesome. This concept exists in other programming languages. For example, in Java, there's a tool called JDepend. I did a lot of looking for what we have in JavaScript, and the only one I found is a tool called Dependency Cruiser. I have seen that you can do this with a linter, but something that is very cool about this tool is that you can not only say, don't depend on me, but you can also do checks for things like circular dependencies. You can do things like no orphans, so modules that nobody's depending on, make sure those die. And what you can do is you can integrate this into your CI. So that way, anytime somebody pushes code and they're about to violate one of your architectural principles, the build fails. It's the best, right? And not only that, we also, for example, have added this as a Git hook so that even if somebody is about to push it, they are warned, hey, you're not supposed to depend on that. You can also use this concept when it comes to deprecating stuff, you know? Code bases are in a constant state of evolution, and sometimes you're like, I did that. Please don't use it, right? You can put something in here to make sure that people don't depend on things that are now considered to be anti-patterns. So the really awesome thing about this is that you have an automated way to preserve certain aspects of your architecture over time. You don't need to rely on code review for somebody to see this import statement and say, you shouldn't be doing that. So this is really, really, really awesome, and I can tell you that until you have added some kind of forbidden dependency tests into your code base, you don't really know what's lurking there. It's really, really fascinating. So I want to wrap up, and I want to just recap what we have learned today. So the first thing that we talked about is that the real cost of software is in the maintenance. It's not in the initial development of the feature. And the big reason for that is because change is inevitable. Things are going to adapt over time, whether it's new feature requests, the market changes, or even the law changes, and now you need to adapt how your code is working. We can also think about architecture as constraints that enable us. So what are the limitations that we can place on the way that we use code and the way that we use data that will help us to move faster and safer over a long period of time? And finally, there are really small changes that we can make to our applications to make them more resilient. The first thing comes down to thinking in a directional way. So organizing our dependencies so that you don't have this ball of mud, but rather can actually isolate where in my application could there be a regression if I introduce a change right here. The other thing is about being more conservative about code reuse, right? Rather than just saying, it is my duty to make this reusable. Instead, think about what things actually ought to know about each other and avoid brittle code that ends up with a whole lot of branching just for the sake of reuse. And finally, we can enforce our boundaries. We can actually use tests not only to verify the behavior of our application, but also to verify the structure of the application itself. And this is a really powerful pattern. So I just want to wrap up with two very last thoughts. The first one being that I think a lot of people tend to think about architecture on this really grand scale, you know? You think about frameworks, maybe you think about meta-programming or huge abstractions. But the reality is architecture starts in the small, right? So every time you and I are writing features, well, we're making architecture decisions. Anytime you extract something to a function or you don't, anytime you make a new module or you decide not to, these are all architecture decisions, so they also deserve a similar amount of consideration. And the last point is this: you don't have to derive architecture from first principles. I think in the front-end community, one thing that makes it really amazing is that we come from so many different backgrounds. I personally studied Latin in college, so I'm not like formally, let's say, a software engineer when it comes to having a piece of paper, but came into this field from somewhere different. And a lot of people that I work with, that I have collaborated with, come from many, many different backgrounds. And that's what makes it amazing. But at the same time, there is also a lot of history and a lot of lessons learned in other fields, in other parts of the discipline, that I think we have yet to properly incorporate into what we have learned. So I just want to encourage you that there is a whole lot of material out there, and even if the examples are written in a language you don't know, like Java or C++, there are a lot of things we can still learn from other communities, and I think we should really be open to incorporating those ideas. Because nowadays we are being asked to build really big, complex apps with a lot of people, and we deserve not to learn things by ourselves, but actually build on the shoulders of people who came before us. So with that, I want to say thank you for listening, and yeah, would love to talk to you afterwards if you have some thoughts on this topic. Thank you.
Thank you so much for the great talk. We still have time for a small Q&A, so.
Very nice talk, thanks. Regarding all those constraints, beside your technical possibilities, how do you make sure your team lives this in kind of a behavior or a habit, like to introduce those constraints, and they also do it in terms of working on a daily basis?
So I think the important thing is, as I shared at the end, the more that you can automate and put into the CI, the better. So, for example, in my scenario in my company, we are often, or not often, but it happens on a yearly basis. Let's say we are acquiring also new companies. We have a whole bunch of developers, and we need to make them productive in the code base without also affecting other people, and also not have them make a big mess, right? And one of the easiest ways to do that is on the layer of tooling, I think. So how much you can automate and shift left so people are becoming informed about potential violations earlier, I think really helps a lot.
First of all, thank you very much for the nice insights. But the question that I have is when to decide to split components apart. So you have a lot of nice code that you can share. As for a concrete example, you have a search input on many, many pages, and that would be shared across a lot of pages.
Yeah.
But only specific pages have different functionalities in there, which would be business logic in these components. But when do you decide to actually split that like highly shared components apart?
So this is why I think when it comes to maybe a search input, it's really great if you can take the presentational bit and put that into your design system. And the big part or the big win there for me is that these things change at a different cadence. So your application code is being deployed all the time, maybe several times a day or even more. And the design system is something that is updated on a slower pace. So you're able to kind of separate these elements that change at different speeds. So in that way, it also removes some of the friction. So I think if you can put the presentational bits there and then leave the business logic actually to the components that are using it, I personally opt for a really highly separated mode of working. And I think part of it also comes down to the size of the team and the organization you're in. Because, for example, with me, we have these highly parallelized teams that we don't want to have to communicate all the time. We just want them to be able to work. And so our code structure really needs to reflect that. So I think it's kind of this balance. Maybe if you're in a smaller team, sharing code, a lot more code earlier in a smaller application makes a lot more sense because it's going to be more efficient for you. But over time, I think you may end up in a situation where it costs you way more to share that business logic because you have all this communication overhead and shared bugs. So that's at least my experience. I can say we have been pulling these things apart quite a bit over the last year or so as we started to double and triple the size of our development team. And in the end, that was a net benefit for us.
Good talk at first. My question is, how do I differentiate between ball of mud and the modular approach? Like, if I have a project and I have a look at it, how can I identify if I have a ball of mud or a modular?
That's a good question, especially because in JavaScript we don't really have certain things that exist in other languages. For example, having these kind of packages where you can say, here's my stuff that's really private. You know, so I think one of the key indicators here, or at least in the front-end world, is when you're using such a mono-repo approach where you have a public library with a few endpoints, or not endpoints, let's say, but a small public API, you can maybe say, okay, this has a limited surface area and I feel comfortable with that. But ultimately, when it comes to something modular, like truly modular, I think this can be a bit challenging to do in JavaScript. And I know we're going to have a talk later today about micro frontends. And for me personally, that would be a great example of this architecture because eventually you have something that is, alas, no longer a monolithic application.
Last question.
Do you have also cases where you are not able to enforce such constraints and just make them more visible? For example, if you have, camel case in directory names or something, you cannot check this automatically how this should be, and just to make them more visible in PR requests or something like that.
I mean, I think pretty much everything that we consider enforceable in terms of let's say code style or these kind of conventions, we are pretty hardcore about putting this into the linter or making custom linter rules. So we have it set up that our CI will fail the build if the linter fails. We don't have any code formatting rules besides what can be done automatically in Prettier, for example. So I think we just take a really pragmatic approach and automate as much as humanly possible to avoid having these kind of things happen.
Thank you very much. This conference has been gradually getting better for me. The quality of the lineup is usually really, really good, and this is something I'm really saying thumbs up.
They're really trying to get speakers here that are pushing to the future of web technologies.
I just feel like it's a very community-driven conference. It also has a lot of quality, and people are just nice. Hi, my name is Sarah, and this is AgentConf in Dornbirn.
Amazing venue. Austria is beautiful. Meeting all of the people in the community and getting to go and hang out and ski.